thank you all for being here and taking the time. It's a pleasure to be here to talk about some of our more recent work that we've released in the last year. And this is really around the scaling of photonic integrated circuits to terabit and multi-terabit levels. So that's what I'll talk about today. And upfront want to acknowledge that this is based upon contributions of a fairly broad Infinera team. And that's the data that I'm going to show here is a collection of their work. Just a brief, the beginning of the talk will be a brief summary of Infinera and some of the earlier photonic integrated circuit work at Infinera, but then we'll transition and focus on terabit and multi-terabit devices after that. Infinera develops optical integrated networking systems, and these are based upon having a differentiated photonic integrated circuit and optical integration platform. And we're vertically integrated, meaning we have substrates that come in to the company, and we ship out hardware and software for building optical networking systems. We have systems that span basically the entire range of the optical networking infrastructure from metro access all the way up to subsea. The place where we're going to focus for the multi-terabit PICs are really around long haul and data center interconnect, where the PIC technology has provided a leadership position for Infinera. This is just a summary statement of where photonic integration is, and I think it's undoubted that integration serves to improve size, power, speed, reliability. There were a lot of questions 10 to 20 years ago. Was integration suited for photonics? I think that question has largely been answered, and the question really has moved from should we integrate in the photonic domain to how do we do that, meaning the scale of integration, platforms, and applications. And today what I'll really talk about is the scaling of the integration again to multi-terabits for the high capacity environments. And with that, you'll see that we get, again, the leverage, we leverage a lot of the scale into cost and power and size is really where we get the predominant advantages. Okay. This shows the progression of photonic integration in the network. So these are for commercially deployed networks, and you see that we started with discrete devices, and integration allowed us to move to the next higher data rate, which again is increasing exponentially, doubling every 2.2 years. And it was really by developing the system on chip photonic integrated circuits that we enabled the scaling to continue at this rate. And specifically today, I'll talk about our latest generation of commercial devices at 1.2 terabits per second, and devices that go all the way up to 5 terabits per second, as well as a pathway to 10 terabit per second or more as well. Okay. And this capability is enabled by ability to integrate many types of optical components at significant scale. So the first full system on chip photonic integrated circuits integrated over 50 functions, and today commercially we integrate over 400 functions, and we have a capability of the platform that we're not utilizing commercially yet, but to integrate well over 1,000 functions. So this is a hero device that has over 1,700 functions integrated onto a single monolithic chip. This is the first generation devices that were developed. This is a 100 gigabit transmitter and a 100 gigabit receiver. These use on-off keying. So it's a tunable distributed feedback laser that powers a 10 gigabit electroabsorption-modulator. And then various generations had optical amplification. And then these are multiplexed by an AWG. And then similarly on the receive side, demultiplexed into 10 high-speed photodetectors. These are significant in that they replace many gold boxes and fiber couplings. And were significant from a technical perspective in that they were the first fully integrated commercial optical system on a chip. They were the first commercial fully integrated multi-channel transmitter and receivers, and they enabled for the first time that we can take the advantages of integration in the photonic domain and realize those at the system level. And these devices continue to be deployed in the network, and just some of their characteristics. Now we're at over 2 billion field hours without a failure, so this is less than half a fit, which is comparable to single submarine lasers that are deployed as well, albeit these are, between these two pairs of devices, it's well over 60 functions. As we continue to scale the capacity, there's multiple domains, and I'm going to talk about moving into the coherent domain. And so we can continue to scale baud rate. We can continue to scale modulation formats, and we can continue to scale number of channels. And in doing so, what is significant is that really photonic integration and the ability to scale number of channels is really what enables us to get to terabit and multi-terabit types of capacities. And what you see is that coherent devices have started with QPSK, and today we'll talk about devices that are utilizing 16 QAM as well as 64 QAM. It's important to recognize that because of the sensitivity of the higher modulation format to phase noise and other impairments, that we reduce reach substantially. So, we're maybe 1/10 of the reach at 64 QAM as, or even less than we are in a QPSK format. So today, solutions that are developed typically tend to be modems that have variable modulation formats, and that's what you'll see today as well in these solutions. This is the first coherent photonic integrated circuit that was developed, and these are 500 gigabit per second transmitters and receivers. And you see the transmitter chip minus the multiplexers shown here, as well as the receiver. And these devices were significant in that they were the first fully integrated transmitter and receiver, not just commercial, but the first fully integrated transmitter and coherent receiver, period. First fully integrated multi-channel coherent device. And then the first commercial use of the indium phosphide Mach-Zehnder modulator for coherent modulation. And that's very significant. And if you look at the industry today, has moved to using indium phosphide Mach-Zehnder modulators, but it wasn't obvious back in 2010 or so when we first did this work that those modulators would perform sufficiently for coherent modulation. So I'll talk a little bit about what are some of the challenges to be overcome today and the results of those. Okay. So I showed this last year, and this is just a refresher for those not familiar with coherent modulation. So this is just showing how QPSK is derived optically. So we start with a laser source, we split this into two polarizations, and then we have a Mach-Zehnder that will modulate the phase between 0 and 180 degrees. We perform a pi/2 phase shift on a second Mach-Zehnder, and then we combine these to obtain the QPSK constellation. And then there's a separate set of data that is also put onto a second polarization, and then this is then rotated and then combined prior to sending the information down the fiber. So that's how the coherent transmitter works. The receiver in coherent is unique in that instead of just detecting the power, I'm able to measure the electric field at the receiver. And that's very powerful for being able to compensate for linear impairments down the fiber, as well as today people are starting to also compensate for nonlinear impairments down the fiber. And just a quick review of how optically we obtain the electric field. So we have an input signal, and then we have a local oscillator. These are then our We take the two orthogonal polarizations from the input signal and mix these with 90-degree hybrids. We then get the following mixing terms from the signal and the local oscillator. These then go into a heterodyne receiver with, as part of the heterodyne receiver, we have a set of balanced photodetectors. And what that does is it takes the square of the optical power or signal on each, and then we take the difference. So if you derive the math for that, and then you take, again, the square of that, and then you take the difference, because I have a balanced photodetector, I'm able to get the real and imaginary parts of the electric field, and then I can take that into the digital signal processing chip. So with that, I can then manipulate the electric field, and again, it's relatively straightforward, as many of the impairments like chromatic dispersion, polarization mode dispersion are all linear functions that can be compensated for in the DSP chip. Okay. So a little bit more, I talked about that. One of the things that was an advance that was first done at Infinera was the fact to realize coherent modulation in a commercial setting using indium phosphide modulators. And why is that unique, or why was that a important technology breakthrough? And so if you look, an idealized modulator will have linear phase versus voltage and no loss. And so if I go form that constellation that we just went through from the transmitter, you'll get a very nice square constellation at all 4 points. However, if I have a nonlinear phase versus voltage response, which is what I have in a 3.5 semiconductor, but still no loss, again, I'll get distortion in my constellation as I trace out that voltage versus phase. Similarly, if I assume I've got linear phase versus voltage, but I have loss that increases with voltage, which is also what happens in a 3.5 semiconductor, I will also get distortion in my constellation. Somewhat serendipitously, these actually serve to compensate for each other partially. And this compensation, plus doing some very specific design techniques in the device itself, enable that we can have an indium phosphide-based modulator, which again has nonlinear phase versus voltage and increasing loss versus voltage, and have sufficiently low distortion in the constellation that we really don't get a penalty relative to, for example, a lithium niobate modulator, which has linear phase versus voltage and much less loss versus voltage, if any, in that. So this was the fact that we could do this in indium phosphide was, and actually have that work successfully in a commercial link, was for the first time done with the devices that we developed with the 500 gigabit per second transmitters. Okay. And in addition, once you have this constellation, it's very important that you maintain very tight tolerances on the different aspects of that modulator. So let me give you some simulations that show you some of the effects if that modulator is imbalanced. So if I take the inner modulator, and the effects typically, I'm going to show you, for example, this is if I'm off by 45 degrees in my bias of my inner Mach-Zehnder, and you can see the distortion here. And this is just shown so that you could visually see it. If I have about a tenth of this, so if I'm off by about 5 degrees or so, I can see this in an optical impairment. So this just gives you an idea of the kinds of distortions, but we're sensitive, at least in order of magnitude or more, to these types of distortions. Similarly, if I have a power imbalance between the arms, so if I've got a difference in bias or a difference in loss in each of the arms, and this shows 6 dB, I get additional distortions. And then remember, we have modulators, Mach-Zehnder modulators, and a super Mach-Zehnder modulator. Again, if that outer modulator is even more sensitive. So again, if I am off by 45 degrees, I see even more distortion. And similarly, if I have loss that is by 6 dB in that outer modulator, again, I have even more distortion. So the net of this is we have to have very reproducible and uniform manufacturing processes and designs consistent with this, as well as we have to implement a control scheme for being able to control to very tight tolerances. So for each modulator, and this is not shown in the architecture, but there's tens of controls per modulator to enable this type of balancing and control. And this just gives you some idea of the manufacturing uniformity. So this is 40 Mach-Zehnder modulator fabricated on the same chip that are overlaid on top of each other. So that's what is part of requisite to be able to make devices that perform at this level. Okay. In the 500 gigabit devices, we're enabling in that we're now using multiple waves that get integrated into a line card. And this is advantageous from a commercial point of view in that we can manage these multiple waves as a single unit of capacity. And that can be done not just from a hardware, but from a software perspective. We can bring in all 10 waves in one operational cycle. And we can also, and this is very important, enable the use of the waves in the network by a software license. So many people, so the model is that you plug in one card and then you pay for the waves as you need them and enable them with a software license. So this is a very different way to build a network and to scale a network than what's been conventionally done. And this is one of the things that photonic integration enables. Okay. And these devices enabled the first custom-built data center interconnect card. And so this enabled over 20 terabits per rack. And at the time it was released, which was late 2014, was leading in metrics of density and power. This was really a new market category, and today it's projected in the next 5 years that these purpose-built data center boxes will be a multi-billion-dollar market. Okay. And the 100 gigabit and 500 gigabit devices have been very commercially successful. So this shows that the 100 gigabit devices have captured over 40% of all long-haul ports. And even though we introduced the 500 gigabit devices later, so a few years after the first coherent 100 gig devices were first commercialized, we've still garnered over 25% market share. Okay. So moving on now to the current generation of devices, we've made several advances from the 500 gigabit devices. And first and foremost, we've integrated widely tunable lasers into the platform. And so instead of having thermally tuned DFBs, we now have full extended C-band lasers per channel integrated onto the platform. Because we're now going to have each channel be able to tune over the extended C-band, we no longer can have a spectrally sensitive multiplexer and demultiplexer. So we've now integrated power combiners versus AWGs on the output. And we've improved the performance of the modulators to operate at 33 and 44 gigabaud. And now again, these have to operate for a singular chip over the entire extended C-band and operate under 16 QAM modulation. So more stringent requirements on linearity. The companion receiver chip, again, uses a power demux, widely tunable local oscillators to mix with the signal as well. And again, capability to operate under 33 and 44 gigabaud and 16 QAM operation. And these are integrated now into a transceiver package. And this shows you a picture of the package itself, and it integrates a receiver PIC and a transmitter PIC these are control ASICs to control all those control elements on the modulators we talked about. And we're integrate free space optics to rotate and combine the polarizations coming off the chip. So there's a single input signal or set of input wavelengths and set of output wavelengths into the module. And it's about the size of my fist. And so we have 1.2 terabits of capacity into that size. And this operates at 200 gigabits per wave and 6 waves integrated for each transmit and receive. And these devices were the first fully integrated commercial transmitter and receiver utilizing tunable lasers, the first multi-channel widely tunable laser commercial devices, and the first commercial multi-channel devices to operate at 16 QAM and 33 gigabaud or higher. So going to now talk some about the widely tunable lasers that are integrated into these photonic integrated circuits, and just a little bit of a review of that technology. So the devices are 4 element widely tunable lasers. They use reflection combs in the Vernier effect. And so specifically we have 2 set of gratings that generate 2 reflection combs that are at 2 different frequency spacings. And that allows us to have wide tunability. And so just a quick review, if we start with a continuous grating in Fourier space or frequency space, we get a delta function. The sampling function then creates a comb, and we then shift that comb by integrating these 2, and so that we can center this comb in frequency spacing based upon the pitch of the waveguide, pitch of the grating, sorry, and then the free spectral range is determined, the spatial frequency of the grating comb is determined by the pitch of the repeated grating. And so what you see here is an example, and so these are the reflectivity spectra from 2 different combs. So a front comb in red and a rear comb in blue. In this case, they're about equal reflectivity. They can be designed differently, and there's a lot of physics that can go into the laser design here. You can modify the shape of this comb, and you can change the reflectivity. But and what you see here is that by aligning these 2 combs, we can have a single frequency be selected. And a key design criteria then is, how much do I misalign the other combs? Because that misalignment is what gives me my side mode suppression ratio. And similarly, I need to design these combs so that as I tune them, I can also tune continuously without hopping from comb to comb. And so a little bit more about that. And so if you look at changing the index of and you can do this by thermally or by injected current, of a left reflector versus a right reflector, I can tune. And if I tune both of these together, or let's start out with, if you tune these differentially, I can then hop basically from reflection peak to reflection peak. Whereas and so that's differential tuning. And if I tune them together, I can continuously tune in between reflection peaks. And then similarly, what I have to do is I have a phase section within the cavity that allows me to make sure I continuously tune to maintain my round trip resonance condition in the cavity. And so specifically then I can get continuous tuning along this tube where I'm biasing a left reflector and a right reflector, and then also compensating the phase, so my 2 pi round trip gain condition satisfied. So those elements are all essential to the design of these widely tunable lasers. Okay. So this shows some results for devices that are integrated into these 1.2 terabit photonic integrated circuits. So this shows a transmitter, and so you can see that we've got continuous tuning across the extended C-band, and we can maintain over 45 dB side mode suppression ratio. And then you can see these wavelength maps that we just talked about. So again, this is the change in index of mirror A versus mirror B, and you see all 6 channels, and you can see that we can continuously tune all the way across the extended C-band. And we can do this both for the transmitter PIC as well as the receiver PIC. And this just shows a little movie showing the actual changing the bias, and that we're tuning all 6 channels across the extended C-band for the 1.2 terabit transmitter.
Is this measured?
Yes, this is measured data. Right. So, and this was before, this data was taken candidly before we had all of the control circuits worked out. So this was measured on a bunch of discrete points and then plotted into a movie. But we can actually do this continuously now with the control circuits. An important, very important metric for Coherent is having low phase noise. So we want to make sure that there's, in those constellation diagrams that we showed earlier, phase noise contributes to degradation in the optical link, in the optical link performance. And so it's very important, especially as I go to higher order QAM modulation formats, to have low phase noise. And so what this shows is 2 things. This is across all 6 channels that we can obtain better than 200 kilohertz. This is phase noise, and you can convert that to line width, but this is better than 200 kilohertz for all 6 channels. And this is in the middle of the C-band, but you can also see across the C-band, I can also similarly maintain better than 200 kilohertz of line width. So we're able to integrate these devices without feedback effects that degrade the laser performance. Another innovation that was applied in this generation of devices is the use of subcarriers. And specifically, what subcarriers are is we take a single wavelength and we split that then into multiple subcarriers or frequencies. And what that allows us to do is operate each of those subcarriers at a lower baud rate. And those lower baud rates have lower penalties to nonlinear effects. And effectively then I'm able to operate at higher launch powers, which means I can get better performance. Here is the specific implementation in the 1.2 terabit PIC. So what you see here, and these correspond to the optical spectrum. So they're heavily pre-shaped by a DAC as the input to the modulator. But we have not just each single carrier that's heavily pre-shaped, but we have a subcarrier, and you can see these subcarriers. And so here's a blow-up of those subcarriers, for just a single wave. And you can see that on each subcarrier, we have its own constellation imposed upon it. So each wavelength doesn't have a single constellation, but has actually 4 constellations per polarization. And with that, we're able to get significantly lower penalties and better optical performance. Okay. So what I show here again is now is each of these modules, and as I said earlier, because of the difference in performance of the different modulation formats, these are designed to operate in a multi-modulation format environment. And so at QPSK, these devices are capable now of over 8,000 kilometers of reach. And that's important because you can now do trans-Pacific types of reaches with this modulation format. And in 16 QAM, we're capable of over to 1,750 kilometers of reach. And these are not hero numbers. These are what you would get in a typical commercial types of deployment. Hero numbers would be much better. There's margin already built into these for what you would have in a real-world deployment. And then similarly, these are the constellations. And what we're plotted here is only the outer constellation, because those are typically the higher frequency content signals. And they typically have the most distortion. But what you see here again is for all 6 channels, both polarizations, only plotting the outer subcarriers, the 16 QAM constellations for this for back-to-back transmission. So this is from a transmitter loop back to a receiver in a module. Okay.
Well, why did the constellations show up in pairs? You probably already explained that.
Right. So this is the 2 outer subcarriers, TE and TM.
So the ones above where you show the pairs like QPSK and there are 2 constellations?
Right. So this here is just a single, not TE and TM, just here. Right. This technology, like previous generations, is also very capable from a manufacturing perspective. So what this shows is yield data. So this is wafer fab yield data, again normalized to 10 mask levels. But you can see that the 1.2 terabit devices, which have been in manufacturing for not quite a year yet, but enough time to get a baseline, have actually comparable yields to 500 gigabit per second devices and compare well to silicon IC benchmarks, and these were done in the early 1990s. Similarly, from a defect density, so this tells us how many good functional devices we have, not their optical performance, but do they function? From a defect density perspective, we actually, the terabit devices continue to be on the same curve as the 500 gigabit per second devices. And these are at a level that is circa where silicon electronic ICs were in the late 80s. And that's where people were literally integrating hundreds of thousands of transistors onto a single chip. So this is what, from a functional standpoint, we've got considerable room to be able to continue to scale at high yield. And from an optical performance standpoint, and these are just some of the important optical parameters, but threshold currents are very well controlled. The ability to tune continuously across the extended C-band is very well controlled. So very capable devices.
So David, when you do those comparisons, are you comparing the same size of the wafer?
Here, so what we do, oops. So these are not the same size of wafers, right? But what we're talking about, oops, sorry. Defect densities here, right? So in a given chip, if I make it with a given amount of active area, how many defects per square centimeter would I have?
Yeah, because with silicon, you progress.
Sure, but
what size did you have on the phosphide? Is this 2-4 inches?
Yeah, unfortunately, the exact diameter is proprietary, but this is less.
The wafers are 4 inches.
That's a range that many people use for electronic ICs today, right? But this curve is less about can I make millions or billions of transistors. It's millions or billions of ICs. It's in a given chip for a given area. what would my yield be? So in other words, how many functions can I integrate into a given chip of a given size? And that's what this really,
And doesn't count the lasers there.
it does.
It does count.
Yes. Right. So if we want to peel the onion one layer deeper here, what this actually does is it is based upon a given architecture, which means I have so many lasers in a given circuit, et cetera. So if I change the number of lasers to the number of modulators, this curve would look somewhat different. But if you look at, I'm scaling transmitters and receivers, it is an accurate curve. And these devices now are going into next generation data center interconnect. So now we've gone from building cards that had 500 gigabit per second to now over a terabit per card. And what this allows us to do with the 16 QAM modulation and the subcarriers, which are very important because I'm spectrally shaping the signals, I can now have 27.6 terabits of information go down a single fiber. Which is best in class. So if you look at where we've come from 2004, where we had 10 gigabit per second discrete devices, to today, we've scaled the bandwidth by 240x. And that's, we now have engines, and these are quite powerful engines. You can transmit the entire printed Library of Congress from New York to Los Angeles in about a minute. So that's very powerful. But then you might ask, well, why do you need all this horsepower? And it really goes to how we're using data today. And the somewhat astounding fact is the data size of all the Facebook photos are 10,000 times the printed Library of Congress. And each year we generate 18 million times the amount of data that's in the printed Library of Congress. So while these are very powerful engines, there is a need based upon the communications and interconnected world that we have today to have these continue to scale. And so we're not done at a terabit. We need multi-terabits and beyond. And so with that, we continue to push on and further develop the photonic integrated circuit technologies. And this is a demonstration that we did several years ago where we have 2.25 terabit transmitters. And what's notable here is that we've integrated 1,700 functions monolithically onto a single chip. So these are 40 lasers and over 160 modulators, not over 160 Mach center modulators integrated into a single chip. And so we have 2 terabits in this case in a 1 terahertz wide super channel. And again, it's very important that the uniformity of these devices is maintained. So you can see the threshold currents are all within a fraction of a milliamp. The Mach Zenders are all within a 1/10 of a volt VPi from each other. So these are all very important to ensuring the success of these types of circuits. In addition, we've scaled the baud rate, and what this shows is with the same architecture that we talked about for the terabit class commercial devices, we have research demonstrations now integrating 14 channels, so going from 6 to 14, but also operating now at 44 gigabaud. So that gives us a 4.9 terabit total capacity. And what you see here are, again, wavelength maps that show all 14 lasers integrated on the transmitter. And similarly, we can tune continuously and have similar phase noise and line width data for all 14 lasers integrated into the transmitter PICs. This shows receiver PIC characteristics where, again, line width is better than 200 kilohertz, and again, side mode suppression ratio better than 50 dB. And improved baud rate, our bandwidth. So here we've changed the design of the photodetectors and have enabled over 20 gigahertz. This is the S21 bandwidth of the photodetectors, and you see these are 56. So these are only the TM-based photodetectors because the graph just gets too busy if we will overlay all 112. But the bandwidth needs to be about half of the baud rate. And so you see that because we're over 20 gigahertz, we're able to operate at 44 gigabaud. So you see these are 16 QAM constellations for all 14 channels at 44 gigabaud. So that gives us 4.9 terabits of capacity integrated into a single transmitter and receiver chip. But we're not done yet. In the quest to continue to scale bandwidth, we've continued to do work to operate at even higher and higher baud rates. So these are devices now that have a similar architecture. They don't have optical amplifiers on them. These were not any inherent limitation, but we just chose to do that to focus on the baud rate scaling. And with this, we've focused on scaling the modulator bandwidth to obtain over 100 gigabaud operation, and to also be able to scale this to 64 QAM constellations. Similarly, on the receive side, we've again used a similar architecture. These are both two-channel PIC demonstrations, and we've integrated this now, and this is done via wire bonding to a high-speed silicon germanium transimpedance amplifier array. And this is a three-stage design with equalization for this investigation. And again, these are the Mach-Zehnder modulator characteristics overlaid on top of each other. So you see the DC performance of the modulators is consistent with very high performance, over 40 dB of extinction. And again, the lasers operate at around 200 kilohertz of line width. The frequency response of the photodetectors and the modulators has been extended, in this case, to a little bit over 40 gigahertz. This is for the photodetectors, and this is the TIA response as well. And these are all measured using, in this case, we've measured them using 50 ohm terminated probes. Tunable lasers, again, of the same vintage that we talked about earlier for the terabit class commercial devices. And then these were then put into a test bed. So this is first operated at 88 gigabaud, 16 QAM. So this is the two-channel receiver PIC assembly with the PIC and the TIA hybrid integrated. And with that, we have a set of reference optics. So a tunable laser with a lithium niobate modulator and a high-speed DAC. And these are operated at 88 gigabaud, 16 QAM, and over 80 kilometers of fiber. And with that, we have obtained Qs well beyond the FEC error correction rate. And with that, we attain a capacity of over 700 gigabits per wavelength. So this is 88 gigabaud, 16 QAM operation. Okay. And this is the receiver. The transmitter is here. So now, again, we have a reference receiver with a tunable laser and discrete optics. And we have a high-speed DAC that uses a RF probe and biases each modulator. There we again obtain 88 gigabaud, 16 QAM operation. And then we've also done experiments where we've taken the transmitter PIC over 80 kilometers to the receiver PIC. And again, that shows successful ability to close a 80 kilometer link with a Q value of 6.6 dB. Okay. So we've also demonstrated the ability to go to higher modulation formats and higher baud rates. This is at 66 gigabaud, 16 QAM, 66 gigabaud, 64 QAM, and then we've also demonstrated 99 gigabaud QPSK. And we've got additional data that not yet ready to share, but the performance in this range is more limited by the test setup as opposed to the inherent quality of the devices. So expect even better data and more bandwidth per wave coming very soon in these devices as well. So what we truly see is that we're really headed towards solutions that provide a terabit per wave, right? And now if we talk about integrating 6 or 10 channels, we're talking about solutions that have 10 terabit types of capacities, right? So, and you see what we've done is, now over a period of three generations going to 4 generations, we've gone from 10 gig on-off keying to our first coherent QPSK. Today we have commercial 32 gigabaud, 16 QAM. But as I said, we're really headed to terabit types of wave solutions using higher baud rates and higher QAM modulation formats. So just to conclude, in the next 10 years, we're going to continue to see more and more consumption of data and generation of data. And video is going to be a key driver of that. And what that's going to drive us to that we're going to need to have solutions that operate at 1/10 the power and 1/10 the cost. And that's going to mean photonic integration is going to be with us for quite a long time. Right. Thank you.
Questions?
Yes. No, I was going to ask just quickly about I have 2 questions.
Sure.
Which is, what is the thermal stability of these devices? So that's kind of very important for
Sure.
users. Jitter, anything like that? You didn't mention jitter, so I was curious about if there's anything you can comment on jitter.
Right.
And thirdly, I guess it's 3 questions. Why not gallium arsenide and jumping all the way right into indium phosphide?
Okay. Let me try to handle each one of those. So thermally, you'd absolutely have to worry about thermal crosstalk. So there's a number of things that you can do from a design perspective. However, if you look, the economics, because indium phosphide is not cheap, so you really want to have a high density, at a certain point you run out of knobs and you really have to resort to how do you be very smart about how do you control these devices. Because we don't have athermal laser solutions today. So there's a whole series of work that I haven't shown around how do you thermally control and compensate for variations as you tune and modulate and so forth. So that is a very important part of this. I can tell you it's very tractable at these types of densities that we have on the chip today, even at the terabit, and we see these continuing to the multi-terabit levels. Relative to jitter is an important factor. The one thing I could say is that there's multiple combinations of jitter. So for example, you'll get jitter from a modulator driver. You also get jitter from the DACs on the DSP. And so the modulator driver is, and there's other places as well in the chain that you'll get jitter from. But the modulator driver is not the defining limit as to any jitter penalty contributions at this point. So I think it becomes an important consideration when you get into the 100 gigabaud kinds of numbers, but it's still good enough to today to close this 100-kilometer link, which will be primarily for these data center interconnect solutions, and and some of the lower modulation formats will be used for longer distance. So I expect it's going to be an important consideration, but I think from the type of technologies that exist today, it's 100 gigabaud or beyond types of consideration. In terms of why not gallium arsenide, I assume you mean for the optical chips, right? So it all goes back to that we want to operate in the low loss, low dispersion part of the C-band. And because of the band gap of where indium phosphide is, that's what pushes us to indium phosphide. If you really had a short reach solution that you could that you wanted to do with multi-mode fiber or something like that, it you opens up those kind of solutions. But today those have been dominated by VCSELs today.
I guess I was reaching a little deeper into some of the nanostructuring that one could do with on a gallium arsenide platform that could put you in those.
Right. So
in those ranges.
Right. So
It's a
there's
little complex, but then it's a costing element as well between the cost of doing work on gas versus indium phosphide.
yeah. So just a couple comments, and I've learned you never say never, right? But if you look at a gallium, and periodically people approach us around gallium arsenide, interesting devices in gallium arsenide. The thing you have to consider is that this is a platform. So we've got 10 between the transmitter and receiver. We've got 10 different device types. So it has to be advantageous enough not to just give us one better device, but it has to be advantageous enough to think about that you're going to move that whole platform and all the investment in that. And so sometimes we'll see things that look interesting, but they provide advantages on one type of device, and they're not revolutionary enough to think about shipping the whole platform, even if you could deal with the band gap issue itself, right? The other comment around economics, if you look, the gallium arsenide substrate costs are much cheaper than indium phosphide substrate costs, but when you look at the rest of the process, there are multiple epitaxial regrowths, as well as wafer fab processing that is nominally where 90 nanometer CMOS is in terms of number of mask levels. So we have a lot of added cost past the substrate cost itself. And in those cases, the costs look very similar for indium phosphide versus gallium arsenide. Right? So the substrate costs matter some, but they're generally not the driver per se. Probably what would be most interesting is if you could gain the advantages that you could with a direct bandgap semiconductor and more processing capability. Right?
Hi. Fred, these are amazing systems, but they're also very complex. And
Yes.
Before this talk, I wanted to bring in a question of, well, what are the failure modes? So I could understand all that, but you kind of hinted that they don't fail, or at least not the deployed system. So I wanted to ask really about sensitivities. What are the leading edge of the system sensitivities that it's really sensitive to? Phase, noise, other things like that.
Right. So you so there's that's a multifaceted question, right? So you can work your way up from the indium phosphide up through the system. So the indium phosphide is very, very reliable, right? So and that's why we can report statistics like that. There's still fiber couplings are still far less reliable than even with this level of integration, the chips themselves. But all that can be managed still, even with these fairly sophisticated packages that we're using. When you get up to the system level, you would be amazed at the type of failures that occur, and they're often not associated with some very sophisticated type of optical impairment, et cetera. They're the fiber cuts, or somebody used the same IP address for two of the waves, and those are actually predominantly the types of things that occur, and this is why in some ways it's sometimes it's easy to gloss over the advantages you get from this pre-deployment. So, but that has been a real big deal with our customers, because there are so many of these problems that happen in simply taking a card, plugging it in, and making sure that the fiber connections are there and turning it on. So if I have a pre-deployed wavelength that literally I can, with a software license, turn on, it drastically simplifies most of those types of failure modes. And then you get back, then you can get back down to the things that, the more optical, technical oriented types of things there. And typically then when you get to those types of failure modes, there's many of them still in these types of systems are software based. And so it takes several levels to get back to the hardware. That doesn't mean that the hardware starts there, right? So you have to start with, we do a lot of work around making sure that the design is robust. And once we do that, however, it typically is further down, pretty further down the Pareto on the failure modes. So.
Thanks.
I thought it was interesting using the DSP to compensate for aberrations in the fiber. Is that something that's done in real time by looking at modulation statistics, or is that more of a test mode where you hit the fiber with an impulse signal?
No, so it's done real time. There's a very large body of work on this, and these are commercially deployed. These are commercially developed DSPs that are done by 4 or 5 companies now across the industry or more. Today the DSPs are responsible for keeping the lasers in lock. And so there's a technique for doing that, to compensating for chromatic dispersion, compensating for polarization mode dispersion, but even some of these nonlinear impairments. And even some of these impairments that I showed you in the constellations, for example, can be corrected all with the digital signal processing. But this is all done real time. So this means that you need very high sampling rates from your DSP. And that ultimately means that there's a small number of people that can make those types of investments to develop the DACs and the ADCs capable of those kinds of sampling rates. Right.
What's the provision that you guys are doing for different kind of fibers? Because now the future or the geometrically differential fibers, because you're looking at the terabits.
Right.
So what do you think of future?
So there's been a lot of work on space division multiplexing. The thing that confounds us is that trying to understand where do you get scaling benefit from space division multiplexing. So the question is if I have if I run out of bandwidth in my fiber, am I better off deploying another fiber, or better to have a space division multiplex fiber? And so you still require the same number of wavelengths, transmitter and receivers. There's maybe a little bit of scaling that you get in the EDFA pumps, but that's pretty small. So to date, we really haven't seen how space division multiplexing changes the scaling. What we're seeing actually from customers is that it appears that beyond 27 terabits in the extended C-band, people are really starting to be more serious about provisioning outside of the C-band. So today, people are at least provisioning optical line systems with amplifiers that can go to L-band for certain the real high bandwidth customers. And then over time, once those run out, I think there's going to be a push to some of the other bands as well, but it's going to depend upon the characteristics of your networks. So if you have a network in Europe where link lengths are a lot less, the ability to move to the O and E bands, I think are going to be a lot more feasible. If you're doing transatlantic or transpacific, then you're going to have different kinds of solutions. But so far, so our focus has been more around getting the maximum density we can in the C-band, and part of that pre-shaping of that signal is important to do that. That gives us, I think, about 10% more capacity than others. But if you're talking about significant multiples, I think you're going to talk about going outside the C-band or to multiple fibers. But so far, we really haven't seen how space division multiplexing changes that scaling.
Okay, great. Well, let's thank our speaker one more time.
Thank you.